Right, okay. So before going to the main discussion of today's lecture, so I have two announcements. So number one, so many of you asked about quiz, right? So when is the quiz? So definitely like not this week. So if it was this week, so I would have informed you. So not this week. So quiz would be next week. Next week. So first next week at 8, right? Sharp 8. Next Wednesday at 8. So the quiz would cover up to linked list. Linked list. Right. And then after the quiz, there would be Viva. So Viva schedule would be shared later on. So I will create a schedule, not on a Wednesday, next week. So this is Wednesday, right? Viva would be after that, maybe Thursday or Saturday. Right, based on so in Viva, I will ask questions, not just the questions I have given in the quiz, but generally I will ask questions from the things that we have learned. Right. So the quiz and Viva would be next week. And so as I know, so we have another, so this is 26. So next week would be 2nd, and then we have another week or two, like we have another, so after next week, so we will have another week. So I will have another, like so quiz would be on 8 a.m. So after that, so I'll have a lecture to discuss maybe quiz, right? From maybe from 9, right? And then so we can continue that discussion in the following week. We can continue discussion on quiz. So if we have just 2 weeks, then we can cover quiz. Right. So then, and the other thing is, if there's anything left, I have like next semester. So we are continuing data structures and algorithms with a new module, advanced data structures and algorithms. Right. So then there we can talk more So definitely we are going to talk about trees, so more advanced trees, and so if there's anything left, we can talk. Right? So up to linked list, huh? Right? So if you have at least general idea on the linked list, so then that would be adequate, right? Okay. Right. So that's about the quiz and the vibe. Okay. Let's move to the pseudocode. All right. So before going to this one, so I have several questions. I have read several questions from the following. The previous discussions, right? So let's take first. So if you remember stacks, right? So in stacks, so what are the main operations? Can anyone tell me what are the main operations here in on stacks? Yeah. Push, pop. Push, pop. Yeah, peak. Right, peak is also considered, but it's mainly push and pop. So peak. So there are three. Right. So can anyone tell me, right? Okay. So very good. So you remember the operations. Now the real question, so what is the big O value? Or what is the time efficiency of push operation? So now you have to imagine what is push, what we do on a push operation. Right. So there are several answers from Johan, Vidushan, Akila, all are concluded with big O 1. Right. So Jayani, all. Right. So can anyone tell me why it is big O 1? Why it is big O 1? Why when we talk about stacks, why it is time time efficiency is big O 1. Because there is one operation is happen at a time. So what do you mean by one operation? Directly insert elements don't need loops. Yeah. we insert only in front, not end. So don't need to go through that. So Akila says that, and then Arfat, and then Vidushan says because there's one operation is happened at a time. Yeah. Yeah. So what is big O1? Yeah, so Johan says, yeah, you can see the answer, right, on chat, because we don't need a loop through stack. All the operations done are primitive operations. I mean, I know that you have the idea, but in most of your answers, like it is not, I would say, not perfect answers. The reason is correct, but the idea that you are giving is not clear. But I know that you have the idea. Inside you have the idea, but how to express that would be the problem. Like, anyway, you are correct. You are correct. Right. So I don't say you are. So what is big O1? So big O1 means, right? Right. Even based on the size, the time does not change, right? So if you have a stack of 10 items, 100 items, 1,000 items, whatever the items, the time would be the same. So that's the idea of big O1, constant time. Yes. So now, Arfat, you are correct. Inserting one element in front. So the time is constant. That word should be there, constant. Constant time. Yeah. I mean, the idea is correct, even in the previous answers, right? Constant time. This is constant time. So inserting, right? Sorry. Let's draw the stack like this, right? So you insert one item, right? You push one item, right? Usually in our, even in our implementation, so we use an array, right? So we use top, right? So we insert on top. Top index, array के top index එකට අපි value එක දානවා, right? So the size of the stack does not matter. So you always put on into this index, right? Size does not matter. N does not matter, right? It is always constant. Right? That's why it is big O1. So you have to emphasize that when you giving the answer, right? But good. So then, can anyone guess the big O of pop operation? Vitushan says big O 1. Any other answers? Yes, Akila says it is also big O 1, big O 1. Yes. So why is that? So I directly go to the implementation, right? So in like pop, we pop the top item, right? So if we have several elements, right? Suppose this is the top item in our implementation, array implementation. So this one would be so return. So this operation is so always we return the top item. It doesn't matter the size of the array, right? So that's why it is constant. Okay. Yeah. Array के size එක කොච්චර වුණත් යන time එක එකයි. So what about peak? Yeah, it's easy. It is almost same as pop, right? Only difference is we don't return the value. So so we don't remove the value. Right? So otherwise we just I will pick. Right? All these operations are equal one. Okay. So let's go to queues. So what are the operations of queues? Insert, remove, peak, or NQ, DQ, peak, right? So let's go with insert, remove, so in when we talk about queue, like sometimes peak is not so important, right? So anyway, let's go with these three. Right. Again, the same question. What is the big O value of insert of a queue? So I'm talking about general queue, general queue, right? Not priority queue. Right, so the answers, most of the answers, almost all the answers are big O 1. Why it is big O 1? queue is something like this. We have a front here, right? We insert, right? Sorry. So we insert value at back, right? So this is the front. So this is back. Right. So we insert a new item into this position. We always do that. Like so, every time we insert where back pointing at into that index. මේ back කියන එකෙන් indicate කරන index එක තියෙන තැනට තමයි අපි දාන්නේ. ඒතර අපිට කෙලින්ම array එකේ ඒ index එක access කරන්න පුළුවන්. So we can directly access that index. So this is the operation. The size does not matter there, right? So the idea is size of the queue does not matter in this case. So always the size of the queue is 10, 100, 1000, whatever. Always it will take constant time. Right, good, very good. Right, so that's why it is. Right. Then right. This is correct. And then what about remove? What is the big O value of remove? So Akila says right, so here there are two answers. Some people say it is big O 1, some people say it is big O n. Right, so most of the people say big O 1. So Akila says it is big O n. Right, okay, so first I'll ask why it is big O n from Akila. Can you tell us? Okay. So you have already given so it will go till the right. So when you remove, right? So this is how it is happened, right? The front is removed. Then I think so. Your idea would be these values has to be shifted. Is that the reason that you are giving? Akila? So we remove the front. We remove the front. We know where front is. This index is known. So we just remove that value. So that means the idea is like we just return that value. Right. So the returning that value is definitely big O 1. We are just returning that value. Right. Then right. So here is so if you remove if you remember our implementation with arrays, right? So if we use arrays in this case, right? So in this case, we usually use two variables, front and rear, right? We use two variables, so we insert items, right? We insert item at rear. Right. So then there would be this one and so, right? So based on that, the rear would be changed. Okay. Right. Oh, so I'll put rear here. And we have a pointer to front as well. Right. Front would be the first item that we insert. This is the front. When we remove the front item. So we know where front is. So we know this index. Front variable stores that index where front is. Front එක තියෙන්නේ කොහෙද කියලා අපි දන්නවා. So then returning that value would be just, I mean, it does not depend on the size, right? We always have a track of where front is. So then in that case, Akila, so do you think it depends on the size? We just return array front. Right? So this is what we do. Because we don't have to go through the other items to find the front. Yes, Akila. So you thought when we implement queue with linked list. Yeah, so I'll come to that, huh? Right? I'm not saying that your answer is wrong, huh? Right? So I am coming to your answer step by step, right? So in this case, right, it will be big O 1 in this case, right? Okay, so we remove this front. Now there's a problem. Now there's a problem. What we have to do is we have to shift these values, right? If we do this shifting, so think about Q, a real Q. So when once the front person is served or he's removed, so then other people are taking the place of the person going front. So this is shifting. So if we use shifting in our implementation, then yes, it is not big O1. So we do this and we shift. The shifting, right? We don't know how many we have to shift. It would be, the worst case would be, we may have to shift n items. If this is full, suppose this is full, right? So then the size is n, we may have to shift n items. First one, second one. So it would be n operations. It would be big O n. Okay. So however, in our implementation, we didn't do shifting. We didn't use shifting. What we did was instead we use circular queues. If you use circular queue, right, then we don't have to shift. No shift. So we change the front. So now this is front. So now actually in this case, the rear would be here. So then if you want to add more, we can add here. So if you remove, so the front would be moved. The rear would be moved. This is rear. This is front. Likewise, so this is a circular key. Circular key. So let me write it clearly, because circular queue. Right. In circular queue, it is not big O n, again it is big O 1. The size does not matter. We only change the value of front. So this variable value would be changed. It does not so the size does not affect that operation. Right? In a circular queue. So that's why, like, instead of using shifting, right? Right, shifting කරන්න තිබ්බනේ. Shifting නොකර අපි circular queue වලට ගියේ. because of this. So we can achieve big O 1 right. Okay. So now let's come to Keela's problem here, right? I mean, the problem that she's raising. So she has a point. She has a very good point. When you implement the queue using linked list, so I'll just write like this, and then so we may have to have some indications where front is, where back is, right? Okay, right? So if you want to add a new item, we can add the new item. We can just change this. So adding a new item, we don't have to go through these elements. So we know where rare item is. We can directly insert a new item next to that. We don't have to do this, right? So in that case, insert again big O 1, even use linked list, right? So let's see removal. So we remove front element, right? So we just remove this front element. We can easily do that, right? So front 1 would be changed to this, and then we can change the previous fronts next to now. We can easily remove this without affecting any intermediate items, other items. Right, like this is, we can implement this using similar to delete last. Delete last. So, oh, no, sorry, not delete. Insert. අගට එකතු කරන්න insert last කියලා method එකක් අපි කතා කරන්නේ. In a similar manner, we can do that. Right? Insert. The removal, delete first. Delete first method එකකින් අපිට පුළුවන් remove කරන්න. So even in this case, we only have to access the first state. So in that case, it is also big O 1. Big O 1. So in that case, did you get that, Akila? So you have a good point, but we can achieve big O1 for both. So if you, okay, so to explain that, so I will open the linked list. So in this method, right, like if we take this method, delete first, right? In delete first, what we did was, so we define a temp, and then the first item is assigned to that. Then the first item is assigned with first dot next. Then temp next is assigned with null, and then we return the temp. So this is how we deleted the first item. We can do the same. We can use the same method to delete the front item. So if only these steps would be involved. Right? Front item can be deleted like this. Right? So this is the first item. First dot next is assigned. The first is assigned with first dot next. So now instead of it will pointing to the next one, and then so this one can be removed. So in this case, do we have to access the other elements? The second one, third one, we don't have to do that, right? We don't have to do that. Without affecting any other items, we can remove this. Other items even don't know that the first item was removed. පළවෙනි එක remove කරා කියලා අනිත් ඒවා දන්නේවත් නැහැ. අපි කෙලින්ම ඒක මීට අයින් කරලා දානවා. Did you get that? Akila, did you get that? And do you have any questions? So yeah, so there's a question here. So when we add node in front, the first inserted value will go to the end. So when we add node in front, why you insert in front? Why you insert in front? Yes, so if we insert front, then right, so this is the front, right? So this is the front, right? So if you insert new item here, front, yes, then right. So this is the newly inserted item, right? If you insert front, then that problem would be there, right? So Aquila's implementation is something like this. Right. Okay, so here, so we insert in front. So there's a new item. So if new item is inserted, it would be inserted in front of this. So now this one would be something like this, as I understood. Right. Right. So, but here, right? So Aquila, yeah, if you implement like that, right? So you only have, this is the first item, huh? This is the first item, right? So now if you insert a new item, you will insert here in front of that as the first item, right? Then when you want to remove an item, you have to go to this one and this one, and then right, this is the first inserted value, so we have to remove this, right? Right. So I will again, actually this is a good point, huh? Front. So I won't use the word front. I would use first, right? First item would be this one. If you insert a new item, right? So we insert here, right? So the front would be, the first would be this one, right? So if I put indices, like this is the item that we inserted first, this is the second item that we inserted, this is the third node, this is the fourth node, this is the fifth, right? So we insert as the first item. Then if you want to remove item, right? So then if you want to remove, we don't know what is the first inserted item. It is in the it is the last item in the linked list. So we have to go to that through other items. We cannot directly access the last item in this implementation. So then if you want to remove that, we have to go through n items, right? So if you have n number of items, we have to go through all those items. So in that case, in this implementation, limit would be big O n. That's correct. That's correct. Right? But we can make it big O1 with slight, very small change. We can do that with a very small change. What is that? So instead of having just the front item, right? So we can have the rear item as well. Sorry. Instead of using these variables, we can have another variable to store pointing at the last item. So Aquila's implementation, I changed it a small bit, right? So it was a regular linked list, right? I changed it to double-ended linked list. Double-ended linked list. So now we can achieve big O1 because we don't have to go through all the intermediate elements. We can directly access the last. So instead of using first and last for these variables, I can use rear and I can use front in the context of Q. So if we are using a linked list for this case, so we can use this way. So I don't have to go through all these steps. I can directly access the front and then I can remove it. So then, so that's where Aquila's point is correct, because in a regular linked list, we cannot achieve this. This is actually a double-ended linked list. Right? So in that case, right? So if we use regular linked list, so regular linked list, right? It is big O1. Aquila, you are correct. Right? But with slight change, right? If we make it a double-ended linked list, definitely we can achieve big O1. Right? So in that case, others are correct. So when you implement a linked list, so it is good to implement double-ended and if possible, doubly linked list. Right? If you have these capabilities, so then we can add. So that's why it is important. Like, so when I talk about a linked list, you may have asked the question. So linked list is fine. So why we need a double-ended linked list and so on, double linked list. One reason is it is flexible, so we can do a lot of things with that. And the other thing is performance-wise. Performance-wise, we can achieve very easily. We can achieve big O1 here. If you have double N, right? If it is regular, not double-ended linked list, it is big O1. So Akila, you are correct there. And then if it is, so we can have better implementation with double-ended linked list, it is big O1. So is it clear, Akila? Right, okay. So actually, so that's why I said she has a very good point there. Right, so then, so there's a question. So is there any need for doing circular queue operation? Yes, circular queue operation without circular, right? So without circular queue, right? Circular queue implementation. Circular queue, we don't have something called circular queue, right? It is actually when we use arrays, right? When we use arrays to implement queues, then we have the circular implementation of arrays. Circular, actually it is a circular array. We don't call circular queue actually. It is not very meaningful, but sometimes we say that. So, but then we can get the idea, okay, circular queue. But actually, fundamentally, it is only with arrays actually. Right? Because if we don't do that, right? If we don't do that, right? So we have like we insert items, right? We insert items, first inserted item and second inserted item and so on. So this is front of the queue. This is the back or the rear of the queue, right? So then we remove items from the front, right? Always we remove items from the front. So that's the fundamental, that's the definition of a queue. We insert items rear, right? We remove items from the front, right? So in this case, so now there is a vacant place here front, right? So how we can remove that vacant? So there's a one way, right? So we can shift the other items as we do usually in our day-to-day life queues. Like if you are in a queue in a bank, right? When first person is get into bank, so we go to his place, right? Then the person behind me would come to my place. So likewise, we shift, right? But this shifting, it is not a good operation. It is a little bit expensive. So if we shift n items, right? Suppose so all the items are filled. So then we have to shift n items. It will take big O n, right? Big O n. So that's why we do this, right? Instead of shifting, what we do is we just change the front. එහෙනම් අපි තැන වෙනස් කරන්නේ front එක තියෙන අපි point කරගෙන ඉන්න තැන වෙනස් කරනවා. Now we don't have to shift. Other items don't they don't move, right? But in this case, the problem here would be, so when we insert items, right? When now the rear is here. Suppose we remove several other items. Let's remove several other items. Okay. Now front is here. The rear is here. Next item, we don't have a place here. We don't have a vacant place here to put the next item. So that's why we move this rear circularly, right? Like we go. So we put items here and here and here, and then we come back to this same side, and then we put items like these. We remove like this, like circularly. We use all the vacant places, right? So that's why we use circular, right? Even without circular queue, we can achieve big O1. But to use the vacant place properly, right? We use circular manner. Only in arrays, huh? Only in arrays. If we use linked list to implement a queue, we don't have this problem. Okay. So is it clear, Mohammed? Right. Okay. Okay. So we talk about stacks, all are big O1. Based on the implementation in queue, so anyway, insert would be big O1, and then big O1 can be achieved even in remove, but based on the implementation, right? So otherwise, sometimes if you do not implement properly, so it would be big O n, right? And then peak. So what would be the in queue peak? Yeah. So we can achieve with peak O1, but based on the implementation, it could be big O n as well. But we have to always go for the best implementation. So big O1. So we always try to achieve the big O1. It is achievable, right? Right. In so right. Then If we go to priority queue, when it comes to priority queue, so there are same operations like insert, remove, speak. Speak is again not very important, but we can talk about that as well. Right. So priority queue. So what are your answers? What is the big O value of insert? So there's a one answer already, big O 1. Big O n. So any other answer? So what do you say? Like someone else? Insert is big O n. Any other answer? Big O 1. No one say big O 1. No. So Arafat, what do you say? What is your answer? Akila says big O n. Johan says big O n. Arafat says big O n. Okay. Someone else. Diniti, what do you say? So you have many other like big O n, big O log n, big O 1s. There are many. Right? Okay, can anyone tell me why it is big O? Okay, so I will remove this one. Because no one gave that answer. Why it is big O 1? Sorry, big O n. Why it is big O n? So we are talking about priority queues. Okay, so Johan has given a very good answer. In worst case, we need to shift all items which are currently in the queue, right? So what is priority queue? What is priority queue? So priority queue is, so suppose we have several items. All these items are having priorities. So if we are going to insert a new item, The regular queue, we inserted that item at rare, right? So let's draw this. Suppose this is the front, right? This is the first item, second item, and so this is the front. So this is the rear. If new item is, so we have 4 items. If new item is added, inserted, then based on the priority of this item, we don't put it just here. We don't put this item just here. We put that based on the priority. Suppose there are priorities. So the priority of this one would be 12. The priority of this one would be 9. The priority of this one would be 8. Priority of this one would be 5. Suppose the priority of this one is 60. The highest priority queue, the highest priority item would be given the front. So it is like priority queues are like the Sri Lankan system in most of the cases, right? Right. Like so usually in most of the countries, most of the developed countries, so all the people have equal opportunities, right? But the countries like Sri Lanka and like similar countries like developing, I don't know why now whether we can say Sri Lanka that it is a developing country, right? We don't see many developments, right? It's only development. So like we can see is our people, right? So they like, so now the students, so they are learning, for example, for you, so for example, you people, you are learning ICT, and then like there are a lot of people like that. So it's a development, right? And so anyway, like similar countries, so the opportunities are given based on the priority, right? So suppose if you are going to school, like when children are given children are selected for schools, then always there are priority list, right? Right, like whether that student or that child is like so his father or mother is a politician, the parent. So like the powerful children, so they are given the priority. If they have money, they that's another priority, right? And then if they can give like several lakhs to the principal, they don't call it to the principal, but they say it's like for the development of the school. So sometimes they take money, right? So so there are several priority lists. So then if that child's parents are all boys or girls of that school, so then the priority would be given. Likewise, there are a lot of priorities. Then the minister calls, or a letter from a minister would be another priority. So, a lot of priorities. So likewise, like the priority. But in other countries, we don't have that, right? Like, so the politicians or the mayor's child or the laborer's child, right? So both are going to the same school where, which is the closest to your house. They are learning in the same school. So that's how those systems have been developed. And I don't know whether in Sri Lanka we can do that, right? So inserting into a priority queue is a little bit complicated, right? So this has the highest priority, then so we have to put that in front. So we have to put that in front. However, in this case, first we have to check the priority. We have to compare the priority. Right? We cannot just put that here. Right? Highest priority තියෙන එක නා පිටිපස්ස දැම්මොත් ඊට පස්සේ මාර ප්‍රශ්න වෙන්නේ මේ අර ඊට පස්සේ දැන් අපි ඉස්කෝලේ යන කතාව වගේ ගත්තොත් එහෙම එයාව නිකන් ලිස්ට් එකේ පිටිපස්ස දැම්මොත් එහෙම ප්‍රින්සිපල්ට ගෙදර යන්න එහෙම වෙනවා. ඒ වගේ ඇමති කෙනෙක්ගේ ළමෙක් ලිස්ට් එකේ පිටිපස්ස දැම්මොත් එහෙම ප්‍රින්සිපල්ට ගෙදර යනවා. හරි. එඳ මේ so in this case we have to compare. First we have to compare with this one. We have to compare with this one. Compare with this one, and so based on that, so we have to shift, right? If this is smaller, if this item is having low priority than the new item, then this has to be shifted, and then the next one, it has to be shifted. Likewise, we have to shift all these items, and then we put this item in front. So anyway, even we don't shift, but we have to do comparison. So we have to compare all the items. We have to check this one and this one and this one, and so all the items has to be. In this case, if there are n number of items, all the items has to be checked. This is the worst case. In the worst case, we have to check all the items. Right? So Johan's answer is correct, and then there are other answers. It's value add in comparing key value. We want to loop n times for find inserting place. Yes. In a worst case, Vajira, we have to go for n, right? So in best case, sometimes like the new items priority, right? New items priority would be, suppose it is priority would be in this case 2. The priority is 2. Then we compare this. Okay, so now the priority is low. The new item priority is lower than the rare item. No problem. So we can add it here. So this is the best case, right? But when we decide big O value, we have to consider the worst case. Worst case would be big O n. Right. So Jayani has answer when inserting value to the queue because of we doesn't know the particular inserting place, we have to go through all the items in the queue to find the inserting place. So it is big O n. Yes, Jayani, it is exactly correct. So all the answers are correct. Vajira, Johan, and Jayani. Good, right? So this insertion would be big O n. It is array or implementation is array or linked list. So we have to go through this comparison. N comparisons would be there in worst case. So how about removal? When you remove items, how about removal? In a priority queue, when we remove items, yes, in that case, equal the reason is when you are removing, we don't check the priority. Only when we insert, we check the priority. Right? When you remove, we remove the front. Directly remove the front. Right? We have pointer to a front one, so it is equal. So if you use, if you only use regular linked list to implement, so then it would be big O n as in the previous case, but we can achieve big O1 with double-ended linked list. If you use double-ended linked list to implement a priority queue, so then we can achieve big O1. So in peak again, if it is a double-ended linked list, so it would be big O1. So any questions? Actually, I took 1.5, so almost 1.5 hours for this one, but in my opinion, this is very important, right? It's very important, so that's why I took a lot of time on this, right? So if you have any questions, you can ask. Right? Is that all? Right? So we talk about stacks, queues, and priority queues. And then what about linked list? Linked list. So what are the operations of linked list? In regular linked list, so we have insert first. So this is regular linked list. Regular linked list means like without double-ended doubly facilities. Regular. regular linked list. In regular linked list, we have insert first, delete first, so mainly, and then search or find, right? So apart from that, even in this case, we can have delete last. So insert last, delete last. Right. So here, then any insert at any point in any given point, insert and then delete. Insert middle, or so you can use any name for that. Huh? So in these last two functions, right? So it is like we search for an item and we insert next to that. මකරේ item එකක් හොයාගෙන ගිහිල්ලා ඒ item එකේ ඊළඟට එක් තියෙන එක විදිහට insert කරනවා. So we can change its name is insert next. Next to a particular item. First we have to search for that item and then delete item. Delete middle or delete. First we search that item to be deleted and then we delete that item, right? So these are operations, and then display or print values of all items. Display a linked list. So mainly these are the operations, right? So usually regular linked list, if I remind you, so we have access to the first element, right? So we have access to the first element, right? We don't know what is last, right? So in this case, insert first and insert last, delete first, right? So what are the big Go values? What are the big Go values for this? Yeah, insert first, delete first, it would be big Go 1. The reason is we have access to the first element, right? We have access to the first element. We can easily insert a new item as the first element, right? The පළවෙනි එක විදියට අලුතෙන් එකක් print කරන්න පුළුවන් ලේසියෙන්. We don't have to access other n elements. We don't have to access them. We can easily insert. We can easily delete, right? Suppose this is the first element. We can easily delete that. Just pointing to the next one. You can easily remove that without affecting other elements. So the size of the linked list does not matter. So that's why it is always constant operation. We go on. Search or find. Right, or search. So search. It's very easy, right? Not complicated. We go in. In the worst case, you have to search, right? So let's go with the original implementation here. So if you want to search, you have to check this one and this one and this one and this one, right? So it is linear search. In linked list, it is always linear search. So linear search is big O N. In unsorted array, again it is linear. So in sorted array, then only we can achieve big O log n in binary search. But in this case, linked list එකේ හැම වෙලාවෙම අපිට linear search එකකින් යන්න වෙනවා. We have to go through all the items in the worst case, right? අග දක්වා හොයන්න වුණොත් එහෙම ඒක big O n. Worst case is big O n. Right? So then insert last and delete last. Insert last. Yes, both big O n. Because we have to go to the end. If you want to insert new element at the end, so you have to go through all the other items. You have to go to the first item and through that to the second item, the second node, and so on. So then if now we are in the last item, so new item can be added or inserted as the next item of the, right? Because we have access to the first item. So that's the reason. Insert last, delete last, both are big O n. Right? Then, what about insert next? So first we search and then insert. And delete in the middle. We do the same thing. So insert or delete somewhere in the middle. Yeah, somewhere in the middle. Oh, so middle is not a proper word there, because insert or delete anywhere. It could be the first one or the somewhere in the middle or the last one. Right? Insert, delete. So let's go with like common insert and delete. Right? Okay. So both are big O, because we don't know where to be inserted. Right? It is based on our searching for that particular item. Right? So both are big O n. it is same as this searching. So that's why it is searching plus some other additional operations. So we consider it as big O. And display, again, I'm not asking that question because we have to display all the items. So linear, in a linear manner. So we have to go through the list. So the display would be big O, right? Okay, now, so I'm going to change this to double-ended linked list. So previously we talked about regular linked list. So now it is double-ended linked list. So most of the things are the same, but let's remove and talk about these things one at a time. Okay. Double-ended linked list. Insert first and delete first. Right? It won't change. In double-ended linked list, we have access to the first and the last. And we have access to the last as well. That's the only difference. We have access to the last, double-ended. So it would be insert first, delete first. It would be the same. Searching would be unfortunately, searching cannot be changed. It would be big O n. So anyway, we have to go through. In worst case, we have to go through all the items. Insert last, delete last. This would be big O. Right? If you want to insert somewhere here, we don't have to go through all the items. We can directly access the last item and we can insert without affecting, without going through n operations. We can directly do that. It is constant. The other things are same as the regular linked list. The display, definitely it is equal. අනිත් ඒවාට කිසිම බලපෑමක් වෙන්නේ නැහැ. මෙන්න මේක විතරයි වෙනස් වෙන්නේ. Insert last and delete last. Other than that, all the operations of double-ended linked list would be same as the regular linked list. There's a good question. But delete last cannot point to the previous item in the double-ended linked list. Yes, that's true. Yes, I forgot that. So if you delete this, so if you want to delete this, right? then we can directly access this. But we don't know the previous item of this. Yeah, that's true. Then that would be the difference. If you want to delete this, the last has to be this one. That's how we can delete this. But we cannot do that because we can access the last one, but the previous of the last one cannot be accessed because we don't have the previous. So in that case, actually I have to change. Thank you for reminding that. So delete last, actually we cannot directly delete. If it is just double end, it would be end. Delete කරන්න බෑ නිකම්ම last එක මෙහෙම access කරලා. We have to go through the first item, second item, and so on. Right. If it is just double-ended linked list, this would be delete last would be big O end. So, Chandigarh, thank you for mentioning that. Huh? So then, double-ended linked list. Double-ended link, double-ended link. So usually, I told you, like when we are using double-ended, just using double-ended linked list wouldn't be much help, right? So in that case, this would change to others would be same. These things won't be changed. Only this would be changed. Double-ended linked list. So usually it is recommended if you implement linked list, if you want to get the maximum out of the linked list, it is better to have the facilities like double-ended facilities are there. Make sure you implement these when you implement linked list. A linked list, a regular linked list means without these facilities. But usually when you implement, please add these facilities to get the maximum use of linked list. Right? සාමාන්‍යයෙන් linked list එකක් නිකම්ම linked list කියන නමින් ගියත් මෙන්න මේවා දාන්න අමතක කරන්න. මේවා දැම්මේ නැත්නම් linked list එකේ නියම ප්‍රයෝජනෙ ගන්න බැහැ. Right? So any questions? Any questions? Any questions? Right. So actually, my plan was to do the lesson, right? Like maybe pseudocode or recursion, but maybe like and then just finish the lecture earlier But I mean, I don't have much problem doing another 40 minutes or 1 hour, right? Uh, so let's take a break and come back to discuss Sudoku. But it's not just like a complicated thing, but I'll give some guidelines. So some, say like some hints when you are using or writing pseudocodes, right? And then recursion, I mean, there's not much, there's nothing new actually. So you have already done, so there are few examples there, that's all. So other than that, it won't take much time. So my plan is to discuss both these two. So there's a question for the assignment of a linked list. So can we use doubly double-ended linked list, or we use only the normal linked list? Please use doubly double-ended linked list. You can use a doubly double-ended linked list. So if you prefer just linked list without those facilities, that's fine. I mean, I won't remove marks or anything, but the implementation would be a bit difficult, right? You, in some operations, you may have to write so additional steps. Because of that, I recommend you to use doubly double-ended linked list. Right, okay, so let's take a break, like maybe 15 minutes break, and then let's go through the slides, right? So in a relaxed manner, and then we can go through the slides 9 and 10. So, and later on, you can review what you have done in the first semester as well, right? Right, okay. So please come back at 10:20, right? 10:20.